This video will use some animations to help make the central limit theorem easier to understand. The first of these animations looks at a normal distribution that has a mean of 16 and a range of 32 and lets us draw samples of size 5. So the first thing I'm going to do is draw just one animated sample, and you can see that 5 units fell out of the normal curve. Those were the units selected, and then the computer program computed their mean, 14.8, and plotted one block down here on the lower level. When I do it again, it draws a second sample. It's different from the first because the samples are being randomly drawn, and it plots that mean. And I can keep doing this. I draw a sample of 5, the mean gets plotted, and each time I draw a new sample, I get different characteristics. So we can already begin to see something of a pattern here. The sample means tend to be close to the mean of the population, and every time we get an extreme value, like this one here, it's being balanced off by the values that are closer to the center. So sometimes we get extreme values, sometimes we don't. But overall, on average, we're finding that our means are sort of being centered here. So far, I've only drawn 15 samples. The computer lets me draw them several at a time. It won't animate it when I do that. So if I draw 5 samples, it just adds them to the lower level. And I can keep doing that, and as I do, you'll see that more and more of them are coming towards the center. And I can draw 1,000 samples at a time, and then 10,000 samples. And by the time I've drawn all of these samples, we're seeing that the sample means form a distribution that's roughly normal in shape, even though my sample size was only 5. But notice also that the spread, the dispersion of this distribution of sample means is not as wide as the original distribution of means from the population. I can also do this using what's called a uniform distribution. So the mean is still 16, but now the variance or standard deviation is much bigger because scores are equally likely at every place along the range. So when I draw my sample of 5, they're much more likely to be spread out towards the edges than they were before because the edges are now just as common as the center part was. So when I go over to drawing samples 5 at a time and eventually 1,000 at a time or 10,000 at a time, we have the surprising result that even though the initial distribution was uniform, because of that process where the extreme values from one end will be balanced out by values throughout the distribution, that even with this small sample size of 5, you can see them balancing each other out, I end up with a distribution of sample means that's approximately normal, even with a small sample size. Let's go on to look at the second one of our demos. In this demo, we get to compare the effect of looking at 2 different sample sizes at the same time. So I've got a normal distribution, and it's not going to do the animation for this one. It will draw one sample of 10 and one sample of 25 at the same time, and it lets me draw 5 samples at a time. So here's the first 5 samples for each of the 2, and I'll do a few more, so now we've got 25 samples. You can see that the larger sample size is beginning to look normal a little more quickly than the smaller sample size. It also looks like there might be a wider spread. So let's draw 10,000 samples and see what we get. So as we draw 10,000 and then 20,000 and then 30,000, both of these distributions of the mean are looking normal, which we expect because the original distribution was normal. But notice that the spread is much less when the sample size is 25 than it was when the sample size is only 10. Just like I did before, I can also look at a uniform distribution, and here, remember, any of the numbers is equally likely, so I'm getting a broader spread for both of the two sample sizes. And as I get to 30,000, again, both of them are normal, even though the distribution was uniform, and the larger sample size made for a smaller dispersion. When I've got 25 scores, it means there are 24 of them that could balance off one of the extreme scores. If I got a score from one end or the other end of the distribution in a sample size of 10, there are fewer to balance it off. So as the sample size gets larger, the dispersion in the distribution of sample means becomes smaller. Let's look at our final demonstration. This one is designed to help us see just how powerful the central limit theorem is. So we've looked at distributions that were uniform and normal. This one will let me draw my own distribution, and I'm purposely going to make a very peculiar looking distribution. It's going to be not normal. I'm going to leave a big gap. I'm going to make it be bulky up and down in a variety of places. And so this is a completely non-normal distribution. And I'm going to set up my sample sizes of 10 and 25, just as I did in the previous demonstration. And so I'll draw 5 samples, and you can see that they're kind of spread out from this bizarre distribution that I've created. And if I draw a few more, we can see that they really are spread out. Some of those bizarre empty spaces are leaving empty spaces in my collection of samples. Here I am up to 50 samples. It's beginning to take a normal-ish shape. Notice I had to say just normal-ish. If I draw all 10,000 samples, and again, so I'm now at a little over 30,000, even with this distribution that was utterly not uniform, not any particular size or shape, I'm still finding that the means that are computed, balancing off extreme scores wherever they fall, tends to have a normal distribution, and that the distribution becomes more normal with less dispersion as the sample size increases. So the takeaway point from this demonstration is that regardless of the underlying distribution, one of the robust features of sampling for the mean is that I can use my knowledge of the normal curve to predict how likely or unlikely a particular mean for a sample is, even if the underlying distribution was not normal. So unlike the situation for an individual, where I needed to know that the sample came from a normal population, the individual score, here I only need to know that I've drawn an adequate sample size. We'll find in the textbook that 30 is the usual size that we pick for a minimum good sample, but as you can see here, even at 10 and 25, we've got a good approximation to the normal distribution when we draw thousands of sample means, even from a very peculiar distribution. So this is what lets us use the normal curve and various curves like it as a way of discussing the probability of a particular sample, even when we don't know whether the underlying distribution is normal or not.